All right, so part 2 of notes today. Discrete, continuous. Discrete is individual points. Continuous would mean a graph that is connected with a line, maybe a curve. So it might still have those points on there. Trying to make those kind of match. This first one is discrete. There's only the points. If I play connect the dots with them, now it's continuous. Discrete versus continuous. Sometimes people get this messed up, like when you're looking at especially people who don't know math, and they try to present a picture of information. Sometimes they'll connect the dots when it doesn't really make sense to connect the dots. An example would be years versus anything, some farm production of the corn crop. Who knows? Like that would be discrete data. 91, 92, 93, 94. Like those are individual years that have some amount of corn that the land produced. It would not make sense to connect those dots because there wasn't anything going on. Like there was not a 91 and a half year where they collected somewhere in between there. So that's kind of a minor issue, but it's just, it annoys math teachers when people make continuous data out of stuff that should not be continuous data. Okay, graph each equation, determine domain and range, determine whether the function, or whether the equation is a function, is 1-to-1. We're going to skip onto, that's a different word, and then both or neither, that kind of, once we answer function and 1-to-1, we've answered those. So we're just worried about whether it's a function and whether it's 1-to-1. And then discrete versus continuous. So looking at this first one, how do we graph that? Or what shape is that? Let's back up one step before that. A line. And how would you graph that line? What would you use first? Good. The b is -3, the y-intercept is -3, and then the slope is 1/2. So we'll just do a quick rough sketch of that. B again at the -3. And then up 1 over 2, up 1 over 2. So, is it a function?
Yes.
Is it 1-to-1?
Yes.
Oops, function, yes. 1-to-1, also yes. Oh, I didn't mention this earlier. The function is the vertical line test. 1-to-1 on the graph is the horizontal line test. So if it passes both, then it's a function and it's 1-to-1. Do you guys know what shape this is? Parabola. And what does the -5 do to the parabola? Flips it. You know what the 5 does? Takes it, stretches it out. Like, this is basically what we're going to do next. So if you didn't know, it's okay. But yeah, that's a parabola. It's flipped and it's stretched. So we'll just kind of sketch it in because that's good enough to answer our 2 questions. Is it a function? Yes. Passes the vertical line test. Any vertical line we put on there is only going to hit once. Is it 1-to-1? No. Because if we draw a horizontal line test, we hit it twice. Or the backwards thing. If our answer is -4, we don't know, what x value led to that. So if you can't go backwards, it's not 1-to-1. Function notation, I think you're familiar with. Right, whatever's in parentheses goes in on the other side. That's the input. Goes in over there. Sort of random collection of algebra topics here. We did a little bit of this yesterday when we plugged things in. So let's, and it's hard to read, so let's skip that because all you're doing is plug in 3 into H, plug in 2/3 into F, plug in -2n into H. Oh, I guess that one's kind of tricky, so let's do that one. Let's see, I think that says -4x² minus 2x plus 5 for H. So H of -2n means whatever's in parentheses goes in for x on the other side. My input is not x, it's not a number, it's -2n. So -4 times -2n² minus 2 times -2n plus 5. And then we need to clean that up a little bit. So if I square -2, I get 4, and if I square n, I get n². -2 times -2 would be plus 4n plus 5. So -16n² plus 4n plus 5. Again, whatever's in parentheses is the input to the other side. Usually we like a number there because that's what we're used to, but we could put anything we wanted to there and just plug it into the other side. Let's pass on that one. It's too messy. Use the graph to find the values and answer the question. So f of 1, this throws people off even though this is supposed to be the easy stuff. F of 1 means 1 is our input, 1 is our x value. F of 1 needs to be the y value. So if x is 1, then y is 1, and I can tell that from the graph. So it's super easy if you know what you're looking at, but sometimes people get confused, I think because we probably do more equations than graphs. So they're well equipped to plug in 1 and do all sorts of things with it. And then we give them the easy question, and sometimes students panic. What about f of 0? I would accept -2. If you wanted to argue and say it's -1.8, that would be fine too, but I'll say -1.8. But yeah, when you're reading off a graph, I have to give you a little leeway there because it's not super clear. How about f of -2? That's definitely 4 because they put a dot there for us. And f of 2? Running out of colors. F of 2 is... Oh, this is... Well, like, I see where you're looking. But it's not shaded in.
It's not there.
It's not there. It's undefined. Exactly right. It never got there. Like, it's headed toward 5, but it didn't get there. And then lastly, f of -3. Oh, definitely undefined. There's nothing over there at -3. Is 4 in the range of f of x? So is the y value of 4 covered? Yes. Right there. Is 4 in the domain? No, because that would mean an x value of 4, and there's no x's of 4, so that's a no. Okay, lastly, almost there. You know what, let's do the rule first, and then we can go back and do the questions. Domain restrictions occur for, well, two things for us. There's more than two things, but this is one of those places where if we say only two things, that's right for Algebra 2, but then it's not right for pre-cal and calculus and on. So for us, there's two places where domain restrictions occur. They occur for fractions. The denominator can't be 0. You can't divide by 0. So if I look at, well, let's do this example here. What would be a problem? What value of x would be a problem for this equation? Why would negative 6 be a problem? Right, so x can't be negative 6. So that's sort of the shortcut way to say the domain. X can't be negative 6. The fancier way in interval notation, think about a number line. It's everything except negative 6. So negative infinity to negative 6, but don't include negative 6. And then pick up again with negative 6 and go to infinity. Given a choice, you'd probably rather just pick the simpler way to say it. X can't be negative 6. But sometimes we'll ask for it in interval notation. So make sure you understand how to get from sort of not common sense, but the easier answer to a more technical answer. But those are saying the same thing. All the answers except negative 6. So fractions is one spot we have to worry about, because you can't divide by 0. And square roots is the other one. What can't you take the square root of? Let's see. What type of number can you not take the square root of?
Negative.
A negative number. Well, I see what you mean by prime. A prime number doesn't have a nice square root. Yeah. But a negative number you can't even take the square root of. So, square roots must be positive. That might be a better way to say it, because that's how we'll set up the problem. So whatever's under the square root has to be greater than 0. Ooh, what about equal to 0? Can you take the square root of 0? Is there a number that multiplied by itself
0
will give you 0? Yeah. So you can equal 0. You can take the square root of 0. I guess we should be technical and say must be positive or 0. So how you handle that is you take whatever's under the square root and just say it's got to be greater than or equal to 0. So move the 4 over. X has to be greater than or equal to 4. And again, if we don't specify, you probably leave your answer like that because that's easier. If we ask for interval notation, then again, my brain thinks number line and then writes the interval. Probably some of you skipped that step. From 4 to infinity. Start at 4, include 4, and go to infinity. Guessing this domain stuff at the end is the only new stuff that you haven't seen before? No one wants to confirm.
Pretty much.
Pretty much. All right, so that takes us to the worksheet, which now you should be more than qualified to answer all those questions. A lot of plugging in, a lot of function, a little bit of discrete continuous stuff, functions and relations. Again, it looks like a lot, but I think because of a lot of it's just questions, I think it goes quicker than it looks. It ends at, so I guess it's 2 pages front and back. So don't do this. When you get to this page, stop. We'll work on that. We'll worry about that on Monday.